So we're continuing along with some problems based on sections 4.3 to 4.6 in your textbook. Let's see what we can do with this problem. A mass of 1.24 grams of sodium hydroxide is dissolved in water and 2.05 grams of hydrogen sulfide is bubbled in. I don't know if you know hydrogen sulfide gas. It smells like rotten eggs. It's actually toxic if you get too much in it, but in small amounts, it just smells like rotten eggs. They actually add a little bit to natural gas so that if there's a break in your line in your house, you'll smell rotten eggs and know to get out. Okay, that's just for interest. Here's the question part of the question. What's the maximum possible yield of sodium sulfide? In other words, how much sodium sulfide will we make? So I've got to decide what kind of problem this is. I'm asked to find an amount of sodium sulfide given the amounts of sodium hydroxide and hydrogen sulfide gas. So what I see here is that I'm asked to relate the amounts of different substances. And that is my cue that this is a stoichiometry problem. I'm going to have to relate the number of moles using the mole-to-mole ratio from the balanced equation. Now, this is no ordinary stoichiometry problem. More specifically, I've given you the amounts of two different starting materials, and that's my cue that this is a limiting reagent problem. I have to decide first which one is the limiting reagent before I can use that to decide how much product that I get. Now, I've seen a variety of ways of solving these problems. Any way that feels good to you and you can convey clearly to me is good for me. You may have a routine you already love from high school. Your textbook shows various options as well. But the way I'm going to do it is the same way I talked you through the ham sandwiches at the end of the last video. So here I go. First, I'm going to determine the limiting reagent. And I find if I write just a few words of clarification, I can guide myself more easily through the problem. What I did with the ham sandwich analogy is I asked if I had enough bread to use up the ham, or vice versa. Now I'm going to ask myself if I have enough hydrogen sulfide to use up the sodium hydroxide. And it's not masses I relate that way. The balanced equation gives me ratios of moles. So I want to see how many moles of sodium hydroxide I have, and therefore see how many moles of hydrogen sulfide that I need. So as I said before, I'm just going to have a few words of clarification. I'm going to say that I have so many moles of sodium hydroxide. I want moles of sodium hydroxide, but the question gives me 1.24 grams of sodium hydroxide. Now, this is not how I did it in high school, but I am so convinced that I love dimensional analysis, I'm going to use it again here. I have to get rid of grams of sodium hydroxide, get moles of sodium hydroxide. Units go first. They tell me what number to go get. Grams and moles, moles and grams. Molar mass, the mass of a mole. So grams of sodium hydroxide in the numerator cancel grams of sodium hydroxide in the denominator and leaves me with moles of sodium hydroxide. Woohoo! To the three significant figures I'm allowed, that's 0.0310 moles. My calculator says 0.131 without that final zero. But if you lose significant figures halfway through, you're in trouble. Once you lose a digit, you can't get it back. Your calculator's not as smart as you are. All right, I have that much. Now let's see how much hydrogen sulfide I would need to use that up. I said need there. I could also say would react with. And I want to get moles of hydrogen sulfide. All right, dimensional analysis is my friend. Get rid of moles of sodium hydroxide. Get moles of hydrogen sulfide. And mole-to-mole ratio, where do I get those numbers? That comes from the balanced equation. Whoops, H2S, not H2O. I have 1 H2S for 2 sodium hydroxide. 1 H2S for 2 sodium hydroxide. So that means I would need 0.0155 moles of sodium hydroxide. Well, do I have that much? Hey, I don't know yet. The question tells me how many grams, not how many moles. But we know how to fix that. How much hydrogen sulfide gas do we have? Well, 2.05 grams. We want to get rid of grams and get moles. And H2S. Units tell you what number to go to get molar mass of 1 mole. And I already calculated that. That's 34.09 grams. All right, so on my calculator, 2.05 divided by 34.09. I'm going to store it in my calculator memory so I don't get round off our error later if I need that number again. To the 3 significant figures I'm allowed, 0.0601 moles of H2S. And you can see why it's so important that I have different labels here, need versus have, because the units on these quantities are the same. So I need those other labels to tell me the different meanings of those two numbers. We've been rattling along mechanically for a while now. Let's pause and bring our higher level chemical judgment back. I would need 0.0155 moles of H2S to use up all that sodium hydroxide. And I have more than that. I have more H2S than I need. That means the H2S is in excess. I have more than enough. H2S is in excess. Some will be left over when this reaction is done. That means that the sodium hydroxide is the limiting reagent. Now, I solved this problem by figuring out how much hydrogen sulfide I needed to react with the sodium hydroxide. You could have gone the other way. You could have started with the hydrogen sulfide and asked yourself how much sodium hydroxide you would need. You'd get the same limiting reagent no matter what. The truth is the truth. All right, so now that I know which is the limiting reagent, now I can go on and determine the product yield. So just a few words to keep my solution easy to follow. If you want to make a map, that's great. But just to show you some flexibility, this time I won't. What I want to know is how much sodium sulfide that I get. And I relate that to the amount of limiting reagent, the one that gets all used up, the one that limits how much product. I need to relate the moles of the limiting reagent, sodium hydroxide. So here we go. I had 0.0310 moles of sodium hydroxide. And I want to get rid of moles of sodium hydroxide and get moles of sodium sulfide. Where do I get the mole-to-mole ratio? From the balanced equation. In the balanced equation, I see 2 sodium hydroxides for 1 sodium sulfide. 2 sodium hydroxide for 1 sodium sulfide. Now, I could calculate that and go on in another line, or for efficiency, I could just continue along there. I want to know how many grams of sodium sulfide I had. So I'm going to get rid of moles of sodium sulfide. Grams per mole, moles per gram, molar mass, mass of a mole. And I worked that out already. That's 78.05 grams. So here we go on my calculator. 0.0310 divided by 2 times 78.05 is 1.21 grams of sodium sulfide to the number of significant figures I'm allowed. Ta-da! Now I solved it this way. As I say, there's other ways to do this. Any solution that is clear and teaches your reader is a good solution, but I will say I need to see that you have explicitly used mole ratios to relate different substances, or I'll lose sleep at night. You can tell me about mole ratios as conversion factors. You can tell me in words, but you must make it clear that you considered mole ratios. All right, on to the next problem. Question 3. Hydrogen fluoride is used in the manufacture of freons and in the production of aluminum metal. It can be produced as follows. Now that first part of the question is supposed to be interesting to you. Whether it is or not is up to you. Here comes the question part of the question afterwards. Suppose 6 kilograms of calcium fluoride is treated with excess sulfuric acid to yield 2.86 kilograms of hydrogen fluoride gas, What is the percent yield of HF? All right, what's the question part of the question? It wants to know the percent yield. And my experience is that sometimes in high school people memorize that, which means they can't remember it now. But we don't need to memorize things. We can think them through. We know how to find percentage. Percent is always the part you're interested in over the total times 100%. Let me make an analogy here. Suppose I had 100 unpopped kernels of popcorn and I popped them, but only 78% of them turned into popcorn. The rest just stayed as kernels. What is my percentage yield of popped corn? Well, that would be the part I'm interested in, the ones that popped, 78 kernels, divided by the 100 kernels times 100%, or more intuitively, 78% yield. So what we say is the percent yield is the actual yield, how much you actually got, divided by the theoretical yield, which is the most you could have gotten, multiplied by 100%. Now again, some people memorize the words actual yield and theoretical yield in high school, and they don't know what they mean. You gotta know what it means in your gut. Again, the actual yield is what you got, and the theoretical is the most you could have gotten. In other words, as always, the part over the total. So let's make a map for this. That's the important part. And remember, you're trying to think through ahead of me. Pause often and see if you can get there before I do. All right, what's the question part of the question? I want the percent yield of HF. And I'm going to play, what do you need to know that? When I play that, I play it as literally as possible, by definition if I can. So because percent yield is actual over theoretical, I would need to know the actual yield of HF and the theoretical yield. So now I'm going to go to the question and see if I know those things. The question says it yields 2.86 kilograms. That's how much you actually got. That's the actual yield. Good. Do I know the most I could have gotten? Do I know the theoretical yield? Well, another way to think of theoretical yield, another meaning is, that's the amount that you calculate based on the amount of starting material. That, finding the theoretical yield, is a stoichiometric problem. We have to relate the amount of starting material to the amount of product. So if I want to know the theoretical yield of HF, I'm going to have to calculate that based on the amount of calcium fluoride. Oh, I need to relate the amount of one substance to another substance. And anytime you relate the amount of one substance to another substance, the central part of the problem is relating the moles of one substance to the moles of the other substance. If I had flashing lights, I'd put flashing lights on that. That's the central part of the stoichiometry problem, where I relate the amount of one substance to another substance. All right, let's see if we can hook this up to the bit we already have. I want the theoretical yield of HF. And what's a good unit for that? Well, my actual yield was in kilograms or grams. Yeah, let's get the mass for the theoretical yield. So I need to convert moles to mass. If I know the molar mass, that'll be good. So we're back as far as moles of calcium fluoride. Do I know how many moles of calcium fluoride? No, I know the mass of calcium fluoride. So I could relate the mass of calcium fluoride to the moles, and I hope by now you know the conversion factor that does this. Now, if you're having trouble with problems and you're not doing maps, please, please, please get some help with that skill. I'll see you in my Zoom office hours. Your map doesn't have to look like mine. Anything that works to connect ideas for you is what we're after here. And that is the important skill, because what comes next is just mechanical working the numbers. But let's do that. Now I've got my plan. The first thing it says is I'm going to convert the grams of calcium fluoride to moles of calcium fluoride. So what did it say I had as the mass? 6 kilograms. 6.0 kilograms of calcium fluoride. Now, you could convert that to grams first. If you wanted to call that 6.00 times 10 to the third grams of calcium fluoride, that's great. But I'm going to show you another way. Whatever's true works. I'm going to get rid of grams of calcium fluoride, but I'm going to keep the kilo part. I'm going to convert from grams to moles, which is what my map says I want. Grams per mole, that's the molar mass, which I already calculated, 78.08. So grams of calcium fluoride is going to cancel with grams of calcium fluoride, and I'm left with kilomoles of calcium fluoride. Kilomoles? Sure, why not? If I can have a kilogram, why can't I have a kilomole? All right, now I'm going to go back to my map and continue on from there. But what I'm going to suggest is you calculate the theoretical yield for yourself first to give you confidence. Pause the video. All right, I'm back. Here's my map. Once I have moles of calcium fluoride, I want to get moles of HF. I'm going to get rid of moles of calcium fluoride. I'm going to get moles of HF. So I've got a mole-to-mole ratio. Where do I find mole-to-mole ratios? In the balanced chemical equation. Let's go back and look. Looks like a 1-to-1 ratio. But wait. That equation isn't balanced. Did you notice? You should always check. There should be a 2 here. to balance that equation. So I'm going to have 1 mole of calcium fluoride giving me 2 moles of HF. 1 mole of calcium fluoride giving me 2 moles of HF. Moles of calcium fluoride cancels moles of calcium fluoride, and I am left with kilomoles of HF. Am I done? Let's go back and check my map. All right, I'm here at moles of HF. And now I'm going to find the mass of HF. I'm going to get rid of moles of HF, and I'm going to get mass of HF in grams. Units tell you what conversion factor to get. Grams per mole, molar mass, mass of 1 mole. And I already calculated that. That is 20.01 grams of HF. Moles of HF cancels moles of HF and leaves me with kilograms of HF. Pretty cool, huh? So let me tap that into my calculator. 6 divided by 78.08 times 2 times 20.01. And I'm going to store that in my calculator memory. To the 3 significant figures I'm allowed, that is 3.08 kilograms of HF. And to attach the meaning back to that, that is the theoretical yield. That is the calculated yield, the most I could get if all that starting material reacted. All right, back to the map. What do we need to do next? I've got the theoretical yield. Now I'm going to combine it with the actual yield to find the percent yield. Percent yield is always the part I'm interested in. The actual yield, what I actually got, divide it by the theoretical yield, the most I could have gotten. And see, the part is smaller than the total. So I've got the unrounded theoretical yield in my calculator. I'm going to use that in my calculation so I don't get round off error. And to the 3 significant figures I get, that's 93.0% yield. Now, sometimes when we're doing this in the lab, a student will come to me and say, is that good? And let me tell you, numbers have no moral value. They're not good or bad. They're just true or false. If we did the calculation correctly, the percent yield is 93%, whether you wanted it to be or not. Now, when you're in the lab, you think maybe you're supposed to get 100% yield? No way. Who told you that? Maybe the reaction was actually in equilibrium and it wasn't supposed to go to completion. Maybe when you isolated it, there was some experimental reason why you couldn't isolate 100% of the product. I don't need your yields to be 100%. I will be looking at them in the lab, but I know what percent yield students can typically get for each experiment, so I'm going to be assessing you relative to that. We don't worry about getting 100% yield. All right, time to take another break. I think this video's had enough content. We'll come back and solve some more stoichiometry problems.